How do humans communicate with the universe? How can they perceive and get information from the world surrounding them? Energy is the only way of connection between creatures and the external world. This energy contains data and information which can inform the human from outside its body. Without this medium, the human doesn't have any clue to understanding the universe. Electromagnetic waves are one of the most important conveyors of energy. In other words, these waves carry data and information of the world. Humans can perceive information and communicate with the surroundings with the help of these waves. What is color? Color is one of the most important information in nature, which is transferred in the form of electromagnetic waves. Human's brain has the ability to distinguish between different colors associated with certain wavelength of an electromagnetic wave, which is reflected from an external object. Why do we see objects in different colors? We see different colors because each material selectively reflects certain wavelengths, absorbing all other wavelengths. This selective reflection of distinct wavelengths is due to pigmentation. How can some animals change their color? And how is the color of special objects changing from different angles of view? Do these two objects show their colors just because of pigmentation? No. An apple's color is due to pigmentation, while a butterfly's color is due to its complex structure. There are classes of materials which show colors due to their complex structure rather than pigmentation. These materials are called photonic crystals.
So how do photonic crystals selectively reflect only a certain range of wavelength and transmit remaining range of wavelengths of the incident wave? Let's begin understanding the photonic crystals by looking at the simplest case of a wave entering from one medium and interacting with another medium of a different refractive index. When the incident wave reaches the first interface, part of it reflects off the surface and rest transmits through the medium. The transmitted wave again reflects off the second interface and part of it again transmits through the medium. If both the reflected waves are in phase with each other due to constructive interference, we see a strong intensity of the color associated with that wavelength. Conversely, if the reflected waves are out of phase with each other due to destructive interference, we do not see any color associated with that wavelength. By the same principles, in a periodic 1D photonic crystal, if the waves reflected from all interfaces are in phase with each other, we see a constructive interference. Or if the reflections of all interfaces are in out of phase with each other, we will then see a destructive interference. So what causes the two waves to be in phase and result in a constructive interference, or the two reflected waves to be out of phase and result in a destructive interference? There are two main factors. The first one is the refractive index of the media. If the wave enters from a low refractive index medium to a high refractive index medium, the reflected wave undergoes a phase change of pi. Conversely, the wave enters from a high refractive index medium to a low refractive index medium, the reflected wave undergoes a zero phase change. The second most important factor is the thickness of the medium or the periodicity of a crystal. For a medium of thickness d, the reflected wave will undergo a phase change of 2d cos theta due to the total distance it travelled in the medium. If the thickness of the wave is lambda by 4, the wave will undergo a constructive interference, whereas if the thickness of the medium is lambda by 2, the wave will undergo a destructive interference. So in 1D photonic crystals, if the periodicity is lambda by 4, we will see a constructive interference.
In one-dimensional photonic crystals, the periodic modulation of the refractive index occurs in one direction. An example is the dielectric Bragg mirror. Photonic structures that are periodic in two directions and homogeneous in the third are the two-dimensional photonic crystals, an example being the dielectric rods in an air host. Three-dimensional photonic crystals have periodic modulation along three different axes. They reflect light incident from any direction, behaving as an omnidirectional high reflector. An example is the 3D woodpile structure. One-dimensional photonic crystals are used in anti-reflection coatings by decreasing the reflectance and improving the quality of the lenses. Two-dimensional photonic crystals show total internal reflection in the hollow core in order to propagate light which you cannot see in normal fiber optics. A three-dimensional optical microchip can guide light through air regions in a 3D circuit, such as the sunlight is trapped and absorbed as it flows in different patterns.